Good morning and welcome to the TIARA-IEEE Seminar in Taiwan. Our program will begin in 2 minutes. Please start to take your seat. At this time, we kindly remind you to silence your mobile devices. Thank you very much. Today's event is being live streamed and we'd like to extend a warm welcome to our online participants. And once again, please note that the seminar will begin in 2 minutes. Distinguished guests, respected industry leaders, esteemed scholars, and the dear participants joining us online and on site. Good morning and welcome to the TIARA-IEEE SYW Seminar in Taiwan. And this event is jointly organized by the Taiwan IC Industry and the Academia Research Alliance, TIARA, and IEEE Taipei Section and IEEE Tainan Section. I'm your MC, Tracy Wang. Today marks the very first TIARA-IEEE SYW Seminar in Taiwan. The acronym SYW stands for Students, Young Professionals, and Women in Engineering, symbolizing the three groups of speakers featured in our sessions today. We're privileged to have 6 distinguished speakers, 3 joining us from abroad and 3 from Taiwan, who will share their research achievements, observations, and insights on talent cultivation within their respective fields. And all of this will be centered around the theme, Innovation for Lightweight AI, Technology and Applications. So let us begin by introducing our distinguished guest today. So when your name is called, please give a friendly wave to our audience. So first, please welcome Mr. Cai Zhongping, Deputy Director of Industrial Development Agency, IDA, Ministry of Economic Affairs. Welcome. And Dr. Justin Che, Director of TIARA and also AVP of e-tron Technology. Dr. Wu Zhiyi, President of TSIA and also VP of ITRI. Welcome. And Mr. Calvin Tsai, Director of Digital Transformation Research Institute, Institute for Information Industry, III. Welcome. And also joining us online, Professor Takako Hashimoto, Director of IEEE Region 10, and she's now joining us online. So welcome, Professor Hashimoto. And also Professor Chris Guojun Lee, IEEE Region 10 Awards Recognition Committee, ARC Chair. And also Professor Chen Chun Yao, Vice Chair of IEEE Tainan Section from National University of Kaohsiung. Welcome. And we also extend our welcome to participants from academia, research institutes, particularly from the semiconductor and IC industries. TIARA and ITA members include Yuchuan Keji, ARM, Lingyang Keji, Huabang Dianzi, Lianyang Bandaoti, Synopsys, Honghai Keji, Jingxin Keji, Qorvo, Huatai Dianzi, Semi, 一元素科技、百家泰、先进车系统、MyTech、羚羊创新、阿比特电子、威联通科技、Obit Semi、 列速科技 and 广化科技. So we know that there are so many of you who have contributed your support behind the scene, although we may not be able to acknowledge each of you by name. So please accept our heartfelt appreciation for your generosity and participation. So the first ever TIARA-IEEE SYW Seminar in Taiwan is made possible through the joint efforts of our three organizers and the gracious support we have received from many partners. We want to especially thank express our sincere gratitude to IDA, the Industrial Development Agency under Ministry of Economic Affairs, the advisory agency of this event for their kind support, and also to the International Connection and Innovative Empowerment Program for the semiconductor industry, and Institute for Information Industry, III, for their valuable assistance. We also deeply grateful for IEEE Region 10 for jointly planning this seminar, which forms part of the 2025 IEEE Day series of events. Okay, now, without further ado, please join me in welcoming representative of our organizers, Dr. Justin Che, Director of TIARA, to deliver his opening remarks. Please welcome Dr. Che.
Hello. Good morning, everyone. Friends joining us online, on-site and online. Distinguished guests, speakers, students, and colleagues from IEEE and the TIARA. Welcome to our first TIARA-IEEE SYW Seminar in Taiwan. I'm Dr. Justin Che, Director of the Taiwan IC Industry and Academy Research Alliance, TIARA, and the AVP of Yitron Technology. It's a real honor to stand here on behalf of our chairman, TIARA Chairman Zhang Shijie, Li Shizhang, who is currently on international duty, and to open this very special event. Let me first extend my heartfelt welcome to our distinguished guests, and Tracy has been covered, and of course, to all the brilliant students and young professionals and women and engineers today, your presence truly make the gathering shine. This is more than just the first SYW seminar in Taiwan. It marks a new chapter where innovation meets imagination. We live in an age where AI is not replacing people, it's empowering dreamers. Every breakthrough begins with curiosity, and curiosity begins with you. TIARA has long believed that technology alone doesn't shape the future, people do. This seminar is a bridge connecting students, professions, and mentors across borders and disciplines. Think of it as a spark exchange, and each idea you share today can ignite someone else's inspiration tomorrow. TIARA was founded in 2016, continuing Taiwan's legacy from the national progress that built our semiconductor strength today, from intelligent electronics to nanotechnology. Our mission rests on three pillars: innovation through industry-academy collaboration. Second, cultivating world-class R&D talent. Third, deploying the next generation of tech leaders. One initiative I'm especially proud of is the high school semiconductor micro course, developed with teachers nationwide and offered free of charge. It's our way of lightening the spark early, because the next great engineer might be in high school right now, just waiting for that first spark for inspiration. Our theme today is innovation for lightweight AI technology and applications. is perfectly timed. We have 6 dynamic speakers, young and mid-career pioneers, sharing cutting-edge research across young professions, women in engineering, and student sessions. What I love about this program is that it reminds us innovation isn't just code or circuits. It's the courage to ask, why not? And the community to try again when things fail. That's the heartbeat of engineering. And one of my mentors once said, technology is built on equation, but progress is built on passion. Let's keep that passion alive today. The journey continues tomorrow at the Taiwan InnoTech Expo 2025, where TIARA will host the Youth in Semiconductor Technology Forum, 青年论坛. If you are visiting us, please join us. Meet startup innovators and visionaries redefine what semiconductor can do for humanity. Before I close, let me leave you with this thought. The future of the technology will be written not only in silicon, but in your imaginations. So dream boldly, collaborate fiercely, and today be the day when one idea, your idea, start changing the world. Thank you very much, and have an inspiring and a joyful journey ahead. Thank you.
Thank you. Thank you, Dr. Che. Thank you very much. Okay, next, may I please invite the incumbent director of IEEE Region 10, Professor Takako Hashimoto, who is joining us online from Japan to give us a few words of encouragement. Professor Hashimoto, are you online? We really appreciate Professor Hashimoto's time because she's actually giving classes in Japan, and she's trying to find time still, try to join us on the seminar. So now please give us a few seconds and let us check whether she's already online and ready to give.
Yes.
Hello, hello.
Hello. Can you hear me?
Yes, we can hear you.
Okay, that's good. Okay. Actually, I want to share my slide a bit. So sorry. Okay. Can you see my screen? Okay.
Yes, we can.
Okay. Thank you so much for everyone. I am Takako Hashimoto. I'm so truly honored to be here. The first SYWC in Taiwan. TIARA-IEEE Seminar in Taiwan. I truly appreciate all the organizing team, including Professor Chen Lee and Chris Lee and Professor Jimmy and Chen, so many friends in Taiwan, and also all the sponsors and speakers for your support. So without your support, I believe we cannot make this event possible. So, and this is a very fast event for the SYW, student, YP, and WE. So it is very remarkable occasion. So I'm truly honored to be here. Okay. So, and actually, just a brief introduction myself. I am a Region 10 director and also the professor of the university in Japan, deputy to the president of Chiba University of Commerce, Japan, and also research fellow of the University of Tokyo. And I used to be an industry researcher. So at RICO is one of the major company in Japan. And also, I got my PhD in computer science engineering from the University of Tsukuba. So, and my research topic is big data analysis, social media analysis. And I have several positions in government, associate member of the Science Council of Japan. And also, I'm working for the Ministry of Internal Affairs and Communications. And Japan Science and Technology Agency is one of the biggest funding agency in Japan. Okay. So, and as you know, IEEE is the world's largest technical professional organization. So actually, we have almost 500,000 members in more than 190 countries. So we are very global community, and we have around 200,000 student members. And our mission is advancing technology for humanity. And we are leading publications and conferences as global leader in standards as well. So therefore, we have a lot of students and student here. So you're part of the IEEE family. If you're an IEEE member, so you will be. So and you are our future to realize IEEE mission. Okay, and IEEE is dividing the world into 10 regions. So this is the IEEE region map. So region 1 to 6 is the US, 7 is the Canada, 8 is Euro and Africa, and 9 is Latin America. And the region 10 here, we are here. So Japan and Taiwan. So we are in the Asia Pacific. So we call this area region 10. So the Asia Pacific region, so we have around 200,000 members. That means the 40% of IEEE members are from region 10, our region. So we are the biggest region in IEEE. That means we have power in IEEE all over the world. And then in 2028, actually, so we are too big, so IEEE decided the region realignment. So region realignment means the region 10 will be divided into 2 regions. So new region 10 and new region 11. So I would like to let you know this information. So new region 10 consists of the North Asia area, China, Japan, Korea, Taiwan, Mongolia, Macau, Hong Kong. So, and the new region 11 is the other area of the Asia Pacific, like this. So therefore, especially from 2028, your presence is more important, getting more important. So we truly appreciate your presence, your participation in IEEE activities, and this is a very important opportunity to get together, work together and know each other and respect each other to develop our career and also strengthen our technical skill as well. Okay. So, and actually, so Region 10 has committee, so to support you. So like this, and also this is large committee, committee, and Professor Chris Lee is here. So he is from Taiwan, and he's my good friend, and also part of the IEEE Region 10 XCOM. So if you are have you have any questions about IEEE and Asia Pacific region, so please contact us. We are always together with you, and we are ready to answer or work together with you. Okay. So this is my address. So and then today's seminar is very important, significant opportunity. So it's not only technical gathering and also the strategic collaboration across the generations, across sectors, students, researchers, entrepreneurs, and the government, industry, academic stakeholders. So, and I'm particularly impressed that this event is co-located with Taiwan Innotech Expo, a global platform of innovation. So let's continue to strengthen ties between Taiwan and Region 10. So, and let this be the first of many impactful collaboration to come. So once again, congratulations on organizing this great seminar. I wish you a fruitful and inspiring event. Thank you so much. Thank you.
Chris Guojun Lee of National Cheng Kung University to say a few words to us. Please welcome Dr. Lee.
Thank you very much to the MC for the kind words. I'm Chris Lee. Obviously, I am the chair of Awards Recognition Committee from IEEE Region 10, and I would like to thank, first of all, Dr. Chue for giving us such a clear vision of what we have in TIARA. And I will also like to thank Takako, who from Region 10 is able to help us reach out. So we are very happy to gather together today. This is the first collaboration between academia, also industry, and also government worldwide. And thank you so much for coming to start with. So we are going to talk about some of the innovations for lightweight AI, both from the technology and the application side. Now, we're all very excited right now, especially during the era of AI and semiconductor. So I would like to share with you that Taiwan is now the global leader of the world's chip supply. And we're very happy to showcase that and to share that with you. Now, this is the numbers that we got in 2022, also from TSRI, also ITRI. In 2022, the global semiconductor market reached US dollars, which is 574 billion, with a growth of 3%. Now, Taiwan, we're happy to share with you that we're #1 in chip fabrication, TSMC, and also #1 in packaging. We are also #2 in terms of the amount of revenue for chip design. Now, we also have colleagues who went to United States for graduate school. Say, for example, for those of us who went to Ivy League, Professor Pei Wenli, who is the immediate past chair of IEEE Tainan Section, we all know that in United States, for these Ivy League schools, they are all on the Route 95. Right, so once you go onto Route 95, you will traverse through all the Ivy League schools, which is the founding academia of United States. We're also very happy to share with you that we in Taiwan have what we call the Taiwan Semiconductor Belt. Because if you go onto the national highway from the north to the south of Taiwan, you can see that we in this country, we can build ICs from scratch, zero. We can have all these, we have the fabrication, we have the IC design house. So you see that the representatives are like MediaTek, Realtek. We also have Novatech, just to name a few, and MXIC. We also, of course, have TSMC, and you see that we have packaging. So welcome to Taiwan, for those of you who are here the first time. You see that we are traversing, as you go from north to south, everything is possible, especially for IC in Taiwan. So yes, what we're gathered here together is to connect international talents through innovations, industrialization, internationalization, and internship. So as you can see throughout, Takako was saying that we are trying to advance technology for humanities. Now, starting from the Industrial Revolution, technology changes the social, political, and economical structure of the country. Now, recently, we saw that information explosion was very big, and you see a lot of changes. Now, especially in the new era of semiconductor and also AI, we see that there are other changes that we see. Now we talk about ChatGPT, generative AI, transformers. Recently, people also talk about agentic AI. So both in school and workplace for the students, young professionals, and also women in engineering, what do we need to learn in school and also in the workplace to prepare ourselves for the next few decades? Because when you look at the landscape right now, there is a difference in terms of the machine and workforce modality. So we're trying to connect everybody upon this, especially during this very vibrant era of AI and semiconductors. Now, we can actually see that, now innovation are facilitated by superstar talents. Now, innovation is the key to economics, because without economy, a country cannot be run. And so that is based on innovation. Now, these innovations today, especially in the era of AI, are done by brilliant ideas of top talents. And only top 1% of these researchers are accountable for over 1/5 of the citations that are published. Now today in Taiwan, in Silicon Valley, all over the world, you see that both the software and especially in Taiwan right now, the hardware designers, they are able to make like 7, 8, 9 figures salaries in US dollars in their early 20s. So this is exciting. So you're placing more requirements on the talents. And industry is also eager to invest. Now in the United States, you see a lot of VCs trying to also invest in top talents. And so they're trying to engage leadership in bridging between industry and IEEE. We hope that upon the IEEE platform, we are having a professional networking platform so that everybody, right, the students, young professionals, academia, industry, and all these professional researchers will get together, and including the industry, because they want to look for talents. That's where we can provide them with. Now you see that AI has changed the landscape. How has it changed? In short, AI has further increased the supremacy of best performance. In other words, the best become better when using AI. Now, people who are skillful in AI becomes more productive. Now, people all hear that there is a P university in the United States where the computer science students cannot find jobs. Don't worry about it. But now it's a different landscape because you're not writing codes. You use scripts to generate codes. You use AI to make yourself more productive. This is a different world, okay? And agentic AI also make possible small number of smart talents so that these people, even very, very few people, can form startups and teams which are very productive using agentic AI. And the industry like that. They want to invest. And I think upon IEEE platform, we can link everybody together using this. The other thing is Taiwan's government is saying that in year 2025, we are officially entering an aging society. Japan is already an aging society. But so even if we age, we need to maintain a high innovation, especially in this aging society. So we need to have very, very good AI workers. We have fewer workers, but because of AI, we are able to resolve that problem. So even the same innovation can be sustained with these superstar talents, in addition to the AI chips. So in addition to the government, they're investing so much money into IC design house, into semiconductors, into power facilities. But hey, talents is also another important thing. Without people, you cannot actually run all these things. Now, we also want to talk about internationalization. You see that upon the magnificent 7, okay, that we have, I just want to talk, you see that Jensen Huang, okay, Jensen Huang is from Taiwan. So he's also an immigrant. Now you see that Alphabet, you have Pichai from India. We also have the other Nadella, also from India, Elon Musk, right? So all this is possible because of internationalization. And the other remark that I want to put is that Jensen Huang actually was born in Tainan, and also Lisa Su. So they're both also from IEEE's Tainan Section. So I'm from Tainan Section, and we're proud of that, okay? So yes, we would like to foster international internship. So we would like to identify and scout these international students and try to help them as early in their career as possible. That's why we are inviting the young professional chairs, we're inviting the students also, and we're inviting women in engineering today to come and talk together with us. And personally, I have also been working on internationalization and also internship. So I personally have a trilateral collaboration with MediaTek. And I have a friend in Nanyang Technical University in Singapore, and he has a dual master degree with Technical University of Munich, München. And upon that program, they need to have 9 months internship. So I am collaborating with my friend, and we just had a meeting yesterday, and one of his students is joining this program, and he will do his internship in Taiwan. Now, the other thing is many of the members of TIARA, they are interested in accruing international talents. So I have already made this happen. So after they graduate, say for example from this, all these MediaTek, Realtek, e-tron should have facilities also in, say for example, Singapore, Malaysia. So these students can actually have mobility, international internship, and they can choose to work in Taiwan or their home country, such as in Singapore or Malaysia or other Southeastern Asian companies that were building up upon this IEEE platform that we're talking about today. So yes, we are connecting international talents in the new era of AI semiconductor, and we're engaging global SYW with industry, academia, and research professionals worldwide. Thank you for joining us, and welcome, everybody.
Thank you. Please remain here, and we're going to take a group photo together. Thank you very much. Okay, now we're going to take a group photo to commemorate this very first TIARA-IEEE SYW Seminar in Taiwan. And first, may I please invite the following guests of honor to join Professor Lee here at the front. And we also invite Professor Hashimoto and Dr. Shivakuma and our speaker, Jamika Sudusingi, who are joining us online to take group photos. So now, please welcome Mr. Cai Zhongping, Deputy Director of IDA MOEA. Welcome. And also Dr. Justin Che, Director of TIARA and also AVP of e-tron Technology. And Dr. Wu Zhiyi, President of TSIA and also VP of E3. And Mr. Calvin Tsai, Director of Digital Transformation Research Institute, III. Welcome. And also we have, Professor Takako Hashimoto. She's now already online. She's now the Director of IEEE Region 10. And also Professor Chen Kunzhi from Yangming Jiaoda University, and he's also the Secretary of IEEE Taipei Section. And also Professor Chen Chunyao, Vice Chair of IEEE Tainan Section from National University of Kaohsiung. And we also have Dr. Savitia Shivakuma, Senior Lecturer of Curtin University, Malaysia, joining us online. Okay, and also Dr. Jiang Zhenglong, Executive Director of TIARA. Okay, now may we please invite the staff to hand the hand cards to our distinguished guests. We're going to take several group photos, and this is the first take. Okay, this is the very first seminar here in Taiwan, and we really appreciate all the helps we have received to make it possible. And this is a really meaningful, truly meaningful seminar. All right, please look at our official photographer. One more. Okay, thank you. Okay, yes, please give us a thumb up. We're here in Taiwan, and also may I please invite our guests online. Also, when we take a photo, we have to give us a thumb up. Okay? Okay, thank you very much. Thank you. Please remain here to stay, and our staff, please take the hand cards. We're going to invite more distinguished guests to join us for group photos. Let's please welcome Dr. C.T. Huang Chaozong Jiaoshou, Professor from National Tsinghua University. And also we have the Dr. Ashwala Bandla, Manager of Paxman Coolers Limited. And Dr. W.C. Tuwei-Zhen Jiaoshou, Professor from National Cheng Kung University. Welcome. And we also have Mr. Chamika Sudisingi, PhD student of University of Illinois Urbana-Champaign, UIUC. He's now joining us online. He's going to give a speech later on. Thank you. And also Dr. J.W. Su Jianwei Borshi, Staff Engineer from Industrial Technology Research Institute, E3. Welcome. and also Ms. Grace Wang, General Manager of High Connect. All right, please stay closer to the center. Okay, follow the instructions of our photographer. We want to make sure that we have a very good, pretty photo. Thank you. This is a very special moment. The very first TIARA IEEE SYW Seminar in Taiwan. Thank you, thank you, thank you very much. Please take your seat. We're going to take another photo with everyone here joining us today. Okay? Our photographer is ready at the front. And we want to take the group photo with all of you because of your generous participation that make this event really happening. And now, okay, please look at the photographer, this gentleman here. Show your smile. The more we smile together, the brighter our future becomes. A confident smile reflects a confident future. How confident are you? Please let me see how confident you are. Okay, please give us a thumb up. 帮我们比个赞. Thank you very much. Thank you. Thank you very much. Okay. Now we'll begin our first session of the seminar. There will be 3 sessions, 6 speakers today, and each speaker will present for 20 minutes. Our staff will hold a sign at the back of the room to remind the speakers of the time. Okay, now please join me in welcoming the moderator of the first session, Professor Chen Kunzhi from National Yangming Jiaotong University. Please welcome Professor Chen. With applause.
Okay, good morning, everyone. My name is Kunzhi Chen from National Yangming Jiaotong University, Taiwan. Now let's start the first section, the YP section. We have the 2 speakers, very outstanding speakers. The first one is Dr. Savisia. Let me introduce Savisia briefly. Savisia is a faculty member in the Departments of Electronic and Computers Engineering at Curtin University, Malaysia. And she is specialized in machine learning, deep learning, software engineering, gamma function, signal processing, image processing, gate analysis, biomedical engineering, and education. She also serves as the program coordinators for virtual computing and the head of the training and the development in the Faculty of Engineering and Science and Curtin University, Malaysia. Because of the her schedule conflict, she joined us online. So let's welcome Dr. Savisia on talk.
Hello, am I audible?
Yes.
Awesome. Okay, hello everyone. It's indeed great pleasure to meet all of you all today, even though I couldn't make it in person. I'm really glad that I can talk to all of you online. First of all, a big congratulations to the organizers for the very first IEEE SYW seminar organized by TIARA Tainan Section. And also big congrats to the organizers, especially Dr. Zhang, Prof. Chris, and all the distinguished guests. So thank you. All right, so for today's topic, Prof. Chris asked me to talk a little bit about my journey and about my research on lightweight AI. So starting a little on my journey with IEEE, it all began in 2013, all right, as just a student member. I was a student at Curtin University, Malaysia. At the time, I was doing my bachelor's in electronics and communication engineering, and started as a secretary, then upgraded as the chair. So that was around 2 years as an undergrad student. But what makes me really change the vision about IEEE was a leadership camp which I attended. Just as student members, we all think that a student club is within the university. So when I attended this leadership camp, I got to know IEEE is not just a university level organization, but it is truly global. That makes me go beyond what I do within the university to region, to the section, to global. So eventually I started my PhD in Monash. It was on mechatronics engineering. I'll talk a little bit on my research later. But during my PhD time as a graduate student member, I got the opportunity to volunteer with Region 10. Firstly as the zonal coordinator, and then eventually got appointed as the Region 10 student rep. So under Prof. Under the Region 10, 2017 as the zonal coordinator, and in 2019 as the Region 10 student representative. So that time I met Prof. Chris. Prof. Chris was the industry coordinator for Region 10. So that's where we first met, and I was actually supposed to join Prof. Chris' team as the postdoc later on, but things didn't go. But anyway, we are very happy that we're still in contact and continuing our collaborations. So afterwards, I got appointed as the YP chair in Region 10. That's where I first time got the opportunity to work with the higher grade members. So that's the time I have also graduated as a PhD, and I started my career, early career researcher in Curtin. So from 2021 onwards till now, I am volunteering with the YP community. So first as the Region 10 YP chair, and then as the vice chair of the global committee, and now as the chair of the Young Professionals Committee. So all in all, it has been a very long journey with IEEE, but truly a rewarding one. What makes me continue with IEEE is that the secret cycle I call is that the more you give, the more you get. So the more you contribute, you get more benefits to yourself personally, and also the opportunities to contribute to the society. So on a day job, currently I am a faculty member at Curtin University. I take care of the software engineering program, and I'm also the head of the training and development. So that's a little bit about my journey. But I just want to highlight, before I go deep dive into my tech talk today, I just want to highlight the significance of being part of a professional community. It can be IEEE, it can be any community that of your wish, but it's very important to be part of it. Just from my personal opinion, that as just a normal student member, you start your journey, but then you need at least 10 years to prove yourself, to be an established researcher or an industry profession. But being part of a professional community, contributing as a volunteer leader, you get the opportunity to actually work with big leaders in your field. That's where I met Prof. Chris. That's where I met Prof. Takako. So these opportunities will help you to prove yourself. And that's very important. Through IEEE, I felt that I'm doing a shortcut here. I'm doing a triple jump where it's more easier for me to get these connections and go where I am supposed to be, and also at the same time contribute to the society. With that said, I'll go into my research area first. So I'm mainly researching in the digital health sector. So in my in PhD, so I was mostly focusing on applied AI in biomechanics. So my research was mainly on using sensors on the foot to estimate the entire lower limb motion. That means you don't need any sensors in the lower limb, or you don't need cameras, you don't need laboratory settings, just a sensor in the foot. You can monitor your walking. So that's basically about my PhD. But now I'm upgrading my focus areas to, smart monitoring of motion from wristwatches, to detecting diabetes from biomechanics motions, and so on. So this is one aspect of my research. On the other aspect, I work very closely with industries, working towards Industry 4.0 and now with intelligent agents to Industry 5.0. So here, one of the case studies I'm now going to pick for this session would be on a metal industry where we are developing few systems towards detecting defects, quality control, helping intelligent agents, helping the engineers to make decisions more effectively and so on. So with that, I'll move on to our topic on lightweight AI. So for the past few years, AI was all about, deep learning was the trending topic. Even the application was very simple. Everyone wanted to apply deep learning. So what is deep learning? Means the model layer, very heavy, it's bulky, but everyone was applying deep learning, not looking into the bigger picture of how this can be sustaining in long run in industry settings and so on. That's where lightweight AI comes in as a savior. So in short, lightweight AI is something like you have the accuracy of a deep learning model, but you shield it with a lightweight shield. That means the model itself is lighter but efficient, but at the same time, it doesn't compromise with the accuracy. So this is really a game changer, especially when you want to deploy the AI into edge devices or your mobile and Raspberry Pis and all sort of things. So lightweight AI really make a revolution to get the accuracy at the same time efficiency. So it's low power consumption. You don't need big GPUs and so on. You don't need a small model size compared to the deep learning models and fast inference. You can get the outcomes faster and it runs in edge devices and so on. So there are many lightweight AI models, but to take a case study out, I am focusing on mobile VIT aspect to today's session. So I'm not sure how many of you in the room today are aware of the different deep learning models. So I'm going to give my explanation very high level. So one of the famous deep learning neural networks is convolution neural networks. So what convolution neural networks does is that it's mainly for images. You can even apply CNNs for 1D data, but let's take an image as an example here. So in an image, CNNs, what it does is it takes one patch at a time and it extracts the local information. So if you see that the yellow boxes that goes around the image, this is where it extracts, convolves and extracts the local information. So we call this as partial induction bias. In short, local information. So another deep learning model is like vision transformer. So what vision transformer does is that it extracts global information. So do an accurate prediction or a detection of any application, you definitely need the local, you definitely need the global information so that your predictions, your estimations are accurate. So if you take CNNs alone and VITs alone, it doesn't have, so CNNs doesn't have the global information analysis and VITs doesn't have the local information analysis. So just before going into the next slide, I want to a bit highlight how VITs do the global information analysis. So if you see that image in the VIT transformer, it is being divided into multiple patches. So each patch will be compared with other patches. So the global information is extracted by understanding each image slot with other image slot and where it stands. So there is a comparison happening. So in both CNNs and VIT, there is a lot of computations happening. So when the computations are a lot, the model itself becomes bulky, it becomes slow, it needs a lot of GPUs, and it will be inefficient to apply it in real-time industry settings. So that's where mobile VIT is one of the solutions, but there are more other solutions. But here I'm taking mobile VIT as an example, comes into place where it combines CNN and VIT aspect, that means local and global aspects, but it shrinks it so that it can be applied in an edge device in a real-time setting. So in mobile VIT is a pretty new model. It was initiated or presented by Mehra in 2022, and it is being reported it combines CNN and transformer with less than 5 million parameters. Okay, now in a very high level way, this is the mobile VIT model itself. But if you look into the model, you will see that there is MV2 blocks, okay, the pink color ones, and there is mobile VIT blocks, the green color blocks. So these two blocks are the ones that makes the mobile VIT efficient and accurate. So I'll touch a little bit of the MV2 block. So MV2 block, we call it mobile net. The 2 means version, so mobile net version 1, 2, and 3, the latest one. So here I'm taking mobile net version 2. So there is a very special mechanism in MV2 that makes mobile VIT efficient. Without MV2, mobile VIT is not efficient. Efficient means lightweight. So what happens with MV2 is that there is a depth-wise separable convolution. So what happens here is normally in convolution network, it process all the channels in your feature map one go. That means you need a lot of processing. But in depth-wise separable convolution, what it does is that it processes each channel, extracts the filtering, and then it combines. This way, it's much faster. And then it also has an inverter residual connection. In here, what it does is that it first, so there is a skip connection. So what happens is that first it expands. So in a normal residual, first it reduces the channel, then expands. But in inverted, it expands your channels, and then it extracts the high dimensional features out, then it shrink it back. Something like, imagine that you have a folded paper, you unfold it, you write on it, and then you fold it back and neatly put it. So that's exactly what this residual inverted residual block does. And then it connects all with a linear bottleneck. So here the linear bottleneck means a linear activation. So if you're aware of with deep learning, we have, normally we do ReLU activation, but here they're using linear just to avoid losing any more data, because your feature map itself is very small after MV2. So without MV2, mobile VIT doesn't have the efficiency characteristics. So MV2 is very, very important. And with that, we go to the mobile VIT. Here is that combination of CNNs and VITs here. So CNN gives the local representation, and then you have the global extraction from the VIT. So first the VIT unfolds the feature map, do the transformer processing, compare the position, and then do the folding back again, and then fusion, combine both the CNN and global to give a prediction. So that's pretty much what happens with the mobile VIT. I have described a very high level way so that everyone in the room understands significance of this lightweight model. So I'm not going to explain like how we apply the mobile VIT to the existing industry data set. This is on the steel data set, a steel metal data set to identify defects. So why it's significant here is that as of Malaysia, there is a 200% increase since 2012 on the metal products. So that means manufacturing of metal products is increasing drastically. That means quality control need to be carefully completed. But what happens is that currently, most of the quality controls are happening in manual way. So what happens is that it's time consuming because you check everything manually, and then there is a high chance that mistakes can happen. So what are the manual process? So these are some of the manual process: visually inspecting. So QC engineers just check the products visually, or they use ultrasonic testing, just rub the ultrasonic sensor on the metal, or just do dye penetration, just put a dye, inspect how the dye will like eventually show the visible defects on the metal. So what we are doing here is that we are supporting an industry in Malaysia. This is one of the top industries in Malaysia, to help do the automatic defect detection using deep learning AI. So this is directly connected to Industry 4.0, and we call this as automatic visual inspection. So now, for this, to prove this model, we are utilizing the Northeast University new steel defect data set. Unfortunately, I cannot reveal our existing study data at the moment, so that's why I'm taking this study as an example to show the effectiveness of the mobile VIT. So as usual, as a typical AI model, you get the data, you process the data, you train, validate, test, and that's the whole process of mobile VIT, nothing special there. So once we have done our training and we have tested, you could see the results here that only just 2 misclassified samples compared to the other defect classes. So almost 99% accuracy was achieved from mobile VIT. And you could see the receiver operating curves here. So typically, if you have a good classification, your curve should converge over the 1.0. So you could see that our curve has converted towards 1.0. But I want to highlight here that the accuracy is 99%, and we managed to achieve this with 1.54 G-flops, around 4.95 million parameters. Now, we compared this with the VGG16. So VGG16 is a CNN or convolution model, and we compared this. And what we could see is that the accuracy is same, but the parameters between VGG and mobile VIT is very different. Mobile VIT is 4.92 million, but VGG is 200 plus million parameters. So you could see they can achieve that, the same level of accuracy with lesser parameters. That means you can easily adapt this to edge device to get this rolling in a real-time setting. So this is one case study of the real lightweight models, significance of lightweight models in Industry 4.0. And of course, we are working, this is a classification example, so we are working on a detection models at the moment. We are working on 3D visualizations of these, and then we are working on AI agents, adapting AI agents towards running Industry 5.0, so that the QC engineers just need to chat with an AI agent to get all the details that need about the defects and all about the defects and products. So that's something that we are working on in terms of this area. And I also want to give due credits to my research team in Kertin, Malaysia, the Computational Intelligence Center, and a couple of our representatives are now sitting in the audience today. Professor Geren is leading the CIC Center in Kertin, Malaysia, and our research are mainly on intelligent visualization and also on the digital health sector. So with that, I want to conclude my talk by saying that being part of IEEE is very important in your professional growth, and I would like to use my journey as a testament for that. So with that, thank you so much, and I will also hope the organizers can share the slides, because I have appended some slides about the opportunities with young professionals for your review. Thank you so much.
Yes, thanks for Salvesia's talk. Maybe should we have Q&A? No? Should we have the, maybe we can open one quick questions.
Yes, sure.
No? Okay.
Hello?
Hey, Savvy, I think one of the other function that I have is to ask questions when nobody else is asking, right? Okay, it's interesting that you're doing non-destructive testing. I remember that was my master thesis. Now, are you aware that for NDT, people are also using that for wafer inspection, right? In Silicon Valley, I used to work with Inspec, and in Silicon Valley, we have Tencor and KLA, where they try to inspect the wafers. Now, in Taiwan, in National Yangming Jiao Tong University, there's a professor who is trying to speed up that AI model using hardware, right? So do you also have like visions in, say, for example, in Malaysia in working on these things? Because you're talking about NDT, that's automatic smart maker, right? So is that something that you guys may be interested in also?
Right. So, Prof. Chris, thank you for the question, and it's so nice to hear from you after a very long time. So, in terms of Malaysia, they currently don't have a smart system for NDT. So they do purely on inspection. What I know is that the industry is moving towards smart, we call it AI CCTV, where they want to purely use AI cameras to detect defects. So that's what I know in terms of the direction from the industry's perspective.
One last comment. Also talked to WaveScan's CEO. He's also from Region 10. He's a student from Singapore. He got his PhD from NTU also, right? Your work should be interesting to them. Thank you. Yeah.
Thank you, Prof. Chris.
Okay, so thanks for your speech. Let's move to the next presenters. Professor Cao Zhonghuang from National Tsinghua University. Let me introduce Professor Huang briefly. Professor Huang currently is a professor at National Tsinghua University, and his research interests include computational photographics, solid-state circuits, and computing architecture. And he served many AE of IEEE journals, and also received many honorable awards such as Young Scholar Innovation Awards from Foundations for the Advantage of Outstanding Scholarship in 2020, and TICD Outstanding Young Scholar Awards. So let's welcome Professor Huang's speech.
Okay, thank you, Professor Chen, for your nice introduction. Good morning, everyone. My name is Cao Zhonghuang. I am from National Tsinghua University, Taiwan. And I am very glad to be here to share our ideas and our roadmap regarding deep learning accelerator design for intelligent image processing. And this is my short outline. Okay, it works now. And I will first introduce our ideas about intelligent image processing, and then I will introduce our accelerator design, particularly with our roadmap and one design example. And I believe this is a new era when AI boom meets IC evolution. So on the AI side, we can see from this figure, over the recent 10 years, the AI model sizes have increased by almost 1 million times. So it means that now we can have a lot of AI models to be deployed on edge devices. And on the IC side, we also have seen a continuing improvement on technology nodes in this year, we even can have gate-all-around or nanosheet transistors on 2 nanometer technology node. Not to mention that now we can have a chiplet design and heterogeneous integration. So all of these techniques can boost computing power that we can use on edge devices. So combining these two major technical trends, we believe that there is a research direction called personal high performance computing, or PHPC for short. It means that if we can put PHPC computing power on edge devices like mobile phone, TV monitor, or AI PC, then we can use those powerful AI models on all of these devices. So let's see what we can have if we can do that. So first, the first benefit we can expect is that we will have unprecedented image quality. So suppose you take a picture in a very low light condition here. And usually you will have this very noisy image. So now you can perform powerful AI denoising to recover the image. And you can also apply AI super resolution. Suppose you have these two low resolution images, and you can see we do not have many details over this region. So now we can perform 4 times AI super resolution to recover this image to this one. And recently, we even have diffusion models, and they can recover this image to this one. Okay? So similarly, we can also perform AI deblurring when we take picture over a long exposure time. We will have this blurred image. So we can perform AI deblurring to recover the image. Okay? And the second benefit we can expect is that we can have unseen upgrade skins. So here I want to use an example to illustrate my point. So suppose you bought your cell phone maybe 1 year ago, and it comes with a super resolution capability maybe for this one. When you bought the cell phone can recover this image to this image. But 1 year later, the company may find a better training mechanism or a better training data set. So now they have a better AI model. They can simply update the model parameters to your cell phone to upgrade the super resolution capability to this one. And now we not only can upgrade AI models at any time, we can even add any trainable models to your cell phone by simply uploading new parameters to your cell phone. Okay, so maybe when you bought your cell phone, maybe you only only has denoising, super resolution, and deblurring techniques on it. And now, maybe 2 years later, the company can add this technique called high dynamic range technique to your cell phone. Or they can also add this snowing technique to remove snows from the picture. But in Taiwan, what we need is this one, the raining technique, because we have a lot of rains here. We usually do not have snows. Okay? So this is the second benefit we can expect. And the third benefit we can expect is that we will see unimaginable applications. So suppose you have the picture or the photo of your baby, but you just think he's not cute enough. So you can do style transfer to convert this photo into Picasso painting style. Then you can post this picture to your social media. And you can also do some random scratch like this one and ask AI models to generate corresponding beautiful pictures for you. And this is my favorite application. It is object removing or so-called implanting. And suppose you have the picture of your lovely dog here, but somehow he bites you in the morning and you don't like him anymore. So you can just cut it out from this picture and fill in your newly lovely bear. And we can even expect we can have personal studio on AI PC. I believe that you have already heard the term image generative AI, right? So in this case, we can simply enter this prompt: a cute corgi lives in a house made of sushi. Then the model will generate this picture for you. And better than that, we can even generate a video. So when you enter this prompt, a litter of golden retriever puppies playing in the snow, their heads pop out of the snow, covered in. Then they can generate this, oops, can we play the video? Because I cannot click the cursor here. Yeah, so let's imagine this will be a very realistic video running here. Okay. Just click the video. Okay, so we have seen so many powerful AI models. So the only question remains here is that can we just play the video? Okay, great. So you can see the puppies here. They look very realistic. And this is generated by OpenAI Sora. So we have seen so many powerful AI models. So the only question remains here is, can we put PHPC computing power on edge devices? Okay, so this is my major concern here. Okay, oops. Okay, so now I would like to talk about our accelerator design, and particularly with our design roadmap and one design example here. So my research goal is very straightforward. We would like to design high performance deep learning accelerators for intelligent image processing. And we also want to cover all kinds of AI models. So we start with the traditional dense convolution network models. And now, well, we are moving to the UNet structure-like models, and they usually are accompanied with point and depth-wise convolution plus some global operations. And now we are working on very hard on newly differential models. And our second goal is to, we will try to push performance boundaries of edge computing. So we started with planar CMOS, and now we are working on our chip for using FinFET technology. And in the future, we also want to leverage the chiplet design and heterogeneous integration to boost the computing power that we can use on edge devices. And this is our roadmap. So for the traditional CNN models, we have implemented 3 chips here. So for example, for this CNN processor, it shows the first CNN accelerators, which is capable of 4K Ultra HD resolution generation. And this Vista video is the first chip which is capable of supporting video CNN models. And in this year, this step processor will even boost the throughput to 8K Ultra HD 60 frames per second. And then we move on to the UNet-like structure models. And in this year, we present this EDA chip, and it can generate, it can do very accurate small object detection using efficient DET. And we can even detect, we can support efficient DET D3 level accuracy at about 26 frames per second. And we also have this Catalyst processor, and this will be our design example later. And now we have several research projects on diffusion models. So we are trying to put the large stable diffusion models on edge devices. And as a side note, with the more and more powerful image synthesis capability, privacy will become a very critical issue. So we are also working on that. We are considering on how to implement privacy-preserved AI inference, particularly using homomorphic encryption. Okay, so this is our roadmap. And now I want to use our Catalyst chip to show how we design one deep learning accelerator. So for this processor, we want to support 4K Ultra HD image deblurring to cover this image to this one. But for this image, it will be an 8 megapixel large image. So the blur kernel here actually is very large. So we need wide receptive field. So we cannot adopt traditional CNNs. So in this processor, we support UNet structure to increase the receptive field. And we use these long skip connections to keep local details. And we also apply channel attention to generate global information. So all of these new model structures, they can increase image quality, but they also bring new design challenges, especially on the increased external memory access, or EMA for short, and lowering computing efficiency. So here we do hardware, we do a model hardware co-design. For example, we propose this technique called skip tunneling, and this technique can reduce 90% of EMA for skip connections here. And we also propose look-ahead channel attention. This technique can reduce about 94% EMA for channel attention. We also do optimization for inference flow. So our pyramid layer fusion technique can increase the hardware utilization by about 70% for this UNet structure. And equivalently, we increase the throughput measured in frame per second here by about 1.5 times. And this is our implementation result. So this chip is was implemented in 16 nanometer FinFET technology, and it can support image deblurring at 4K Ultra HD 30 frames per second using only 1.1 watts and 5.1 TOPS, tera operation per second. And we not only built chips, we also built demo system. And to demonstrate the second benefit I mentioned before, the unseen upgrade schemes. So we implement not only deblurring technique on this demo system, we also include denoising and style transfer on our demo. So here I want to share our demo video. So can anyone help? Okay, great. Okay. So this is a joint work with Novatech. Okay, so let's see. So our chip is here, and we connect our chip to this evaluation board, and we adopt its DRAM system and HDMI system on this evaluation board. So here we show the blurred input on the left and the blur result on the right. And we can move this part here in the middle here to compare the results. So we can show we can see the deblurring quality on the right. And we can send the videos into this chip and we process this video in real time. And here we can capture the videos in real time using the camera here. And so now we are capturing the video in real time and processing the video also in real time. And we can freeze the frame here to examine the details to see if the deburring really works. In here, we show the most important instrument in our lab, the sofa chair here. So you can see the deburr results. And now we simply update the model parameters. Then now we can have denoising capability. And here I want to mention that we do not do model fine-tuning. So we just tried to denoise any videos or image we can have to see if we can have some denoising quality here. I think it worked quite well. And we also try to capture videos in a very low light condition and to see if the image can be restored in a nice way. And now we update the parameters again to have these style transfer functions. And here the style is edge style. So we can still change the image or videos to have the image style transferred. And if you have time to come to National Tsinghua University, you are welcome to visit my lab, and we can have you style transferred. And you can choose the style you want to be transferred. And our visitors all like this function. Okay. So I need to move forward. Okay, great. Okay, I will stop my demo here. Oops. Okay, this is my last slide. I want to conclude my talk here. And first, I believe that the AI boom and IC evolution can enable intelligent image processing on edge devices if we can put PHPC computing power on them. Then we will have unprecedented image quality, unseen upgrade schemes, and unimaginable applications. And I believe that there is a lot of research space for researchers to explore here. And our goal here is quite straightforward. We want to provide high-performance accelerators to enable high resolution and high-quality applications. And to achieve our goal, we devise many new techniques, especially to reduce EMA and increase computing efficiency. And we not only implement chips, we also build systems demos for concept prototyping. So I will end my talk here. Thank you for your attention.
Great. Thanks for Professor Huang's nice demo and a nice presentation. We can open one questions before a 10 minutes break. Any audience have questions? Okay, I have one simple question. In your presentation, you mentioned that the current mobile phones may support the function that you can upload the trainable AI. So the AI model is the server based, or the AI engine, AI hardware in a mobile phone can support the trainable models.
Here, what I mentioned is to replace the old model parameters, just the old model parameters.
So you upload the data to
the cell phone, just to replace the old model parameters. Actually, you can even using the same computing power to generate better images in this case.
Okay, got it.
Right, very impressive, Professor. Just one question that I'm trying to ask your advice It's interesting how you go from the vertical, different levels of abstraction, from algorithm all the way till even FinFET. So you were mentioning that you're taping out with 16 nanometers FinFET. Right, so
Yes.
How did you access that process? Now, how much did you pay for it? Because I know, like in US, for UIUC, they pay like $30,000 just for a decent tape out. Right, so do you mind sharing with us how you get access to the advanced process and how much it costs in Taiwan, the overall environment that we have in Taiwan for academia and industry? Yes.
Okay, thank you, Professor Lee. This is a very good question. And luckily, I'm in Taiwan. So we have TSRI, Taiwan Semiconductor Research Institute, and we can do 16 nanometer tape out through them. So we only pay very little because our country will cover most of it. And I also have some direct project with TSMC, so we do not need to pay for that. But I want to mention that TSMC has a promote layer FinFET University program. So I believe most of countries can access 16 or even 7 nanometer technology through this program. Okay, so this is what I can share with you.
Do you accept international interns?
Sorry?
If there are students who like to do internship in your lab, say from Singapore, from Malaysia, from Indonesia, would you accept them?
Yeah, I will consider that. Okay.
Thank you.
Thank you. Thank you very much.
Okay, so thanks for Professor Huang the presentation again. Okay, so because we have a little delay, so maybe we can have the 10 minutes break and please come back to join the next event at 11:05.
Okay, thank you, Professor Chen, and we thank two speakers. Just like Professor Chen said, we're going to take 10-minute break. Please come back at 11:05. Thank you very much. Please enjoy the coffee outside. Thank you. Ladies and gentlemen, our next session will begin in 2 minutes. Please start to take your seat. Thank you. 我们也请外面的工作伙伴麻烦提醒一下今天与会的来宾，我们下一个场次马上就要开始了，请大家开始就座，谢谢。Okay, ladies and gentlemen, welcome back. Now we proceed to session 2, the Women in Engineering session. Please join me in welcoming the moderator of the session, Professor Chen Chunyao from National University of Kaohsiung. Welcome.
Hello, everyone. I'm Chunyao Chen from National University of Kaohsiung. I'm also the officer of Tainan Section, IEEE Tainan Section. In this session, we have two speakers. Let me introduce the first speaker, Dr. Aisha Brenda. Dr. Aisha Brenda, she is a clinical innovation manager of Pesserman Cooler Limited Company. And she is also the principal investigator of the N.1 Institute for Health, National University of Singapore. She is also the chair of IEEE Region 10 Young Professionals. The topic today he will talk is human-centered technology in an AI-driven world, design digital health solutions for supportive cancer care. Let's welcome Dr. Aisha Brenda.
Thank you very much, Prof. Lee, for that kind introduction. Hi everyone, such a pleasure to be here back in Taiwan after a decade almost, and it's always lovely to interact with all of you here. I'm Aishwarya Bandla, and like Dr. Lee was mentioning, I work as a clinical innovation manager in a UK-based medtech company, Paxman Coolers Limited, who develop medical devices for supportive cancer care. I am also part of the National University of Singapore in a couple of research institutes, the N.1 Institute for Health and also the Institute for Digital Medicine, where I serve as a principal investigator and a senior research fellow. In IEEE, my journey, similar to Shavi, started in the Women in Engineering in the Singapore section. I chaired WIE there and then got an opportunity to work with young professionals in Region 10, the committee that I chair now. And I also work with the Global Students Activities Committee and the Young Professionals Committee as a YP rep to the Student Activities Committee. I am a biomedical engineer by training, and today's talk will, we heard a lot of buzzwords so far. We heard about AI, we heard about semiconductor, we heard about innovation, and several different very specialized research topics. I'm going to take a different angle towards medtech and understand how all these terminologies which we heard about, as Dr. Justin mentioned, are enablers for dreamers. So let's see how these aspects can be enabled by another tool, which is design thinking. And I will talk about my journey in digital health and the medtech space as a case study for this. So this talk has several flavors in terms of technology specializations, and this has essentially been my journey so far. So I started with an undergrad in electrical and electronics engineering, had a short stint in software as a systems engineer, went on to a graduate degree in biomedical engineering. So you see how the multidisciplinary, interdisciplinary aspect is already coming through. And more so in an AI-driven world, it is important to have skills across several technologies, and having these enablers connect your skills across these technical specialities. I then went on to have research experience in fields of neurotechnology, oncology, which is essentially cancer care, and also a bit of nanotechnology as a mode of diagnosis and treatment for disorders in neurology and oncology. Finally, it led me to my current work in wearable medtech and also digital health. So let's see how this journey unfolds. So stepping back, the broader theme, like I said, is in the space of a case study in the space of medtech and digital health. So looking at a patient, be it a healthy individual or a diseased individual, when we are looking at prevention, diagnosis, or treatment of any indication, we interact with so many different factors, so many different kinds of individuals, so many different kinds of technology. But as a patient, what is important for that individual is receiving the best care through the best people and the best technology. And that's where we come to user-centric or patient-centric ecosystem. How do we build these technologies, and how do we center these individuals who offer these products and services to be patient-centric and user-centric to get the best technology and the best services to the user or the patient in this case? That leads me to the enabler which I will focus in my talk, which is design thinking. So design thinking is, again, a very interesting tool which can be used across disciplines. Can I have a show of hands of how many of you are familiar with design thinking or use it in your work? There you go, Dr. Cheng. Anybody else who has heard of design thinking methodologies? Okay, well, I hope this will be an introduction to you, and I'm sure you will find the use for it in your work going forward. So the design thinking framework essentially is based on these few pointers, and there are so many different frameworks which are built around these core ideas. So you start with empathizing what the problem is, what the user need is, and this can be any technology, any technological discipline. So it just cuts across as horizontal. identify what is the actual user need that's defined, and then you go on to ideate. So essentially, when as technologists, engineers, we start at ideate, but design thinking forces us to step back and think about what does the user actually need and what is the problem you're trying to solve, and then start ideating towards that. So designing with the end in mind rather than designing and then finding a problem to meet that solution. After you ideate, then you go on to prototype and then finally test the solution. And another key part of design thinking is that it is iterative. Once you do this, you go back into the cycle until you find the best solution which meets the user needs. So let's look at a case study in digital health, which I've been fortunate to work in for the past decade. And this centers around wearable medtech. And all of us have been associated with wearable medical devices in some form or the other. And the most common is a smartwatch or a fitness tracker, and I'm sure most of the room has one on their hand, or some form of wearable medical device which you might be using. However, wearable medical devices are not just restricted to a smartwatch or a fitness tracker. All these are also different forms of wearable medical devices and much more. So you can see even a smart socks. The more common ones are the smart bracelet, smart ring like the Oura ring, or there are so many other variants which are in the market now, and so on and so forth. And these come into play in various sort of indications, medical indications, be it preventive health or for diagnosis and even monitoring treatment of more serious disease conditions. So stepping into the specific disease condition which I've been working with, it's called CIPN, and CIPN expands to chemotherapy-induced peripheral neuropathy. That's a mouthful. Let me break it down. So we are all familiar with, let me skip back a slide. Sorry. Okay. So CIPN is essentially chemotherapy-induced peripheral neuropathy. So chemotherapy is the treatment, most common treatment for cancer care in the current world. And what happens is when patients undergo chemotherapy, they are faced with several side effects. The most common one which we see and associate with chemotherapy is hair loss. That's called chemotherapy-induced alopecia. The other more common, more serious, but often overlooked side effect is CIPN. And what is CIPN? As you see in the image there, the patients start developing numbness and pain in their fingertips and toe tips when they start receiving chemotherapy. And that is a result of this toxic chemicals that are designed to kill the cancer cells, but as a side effect, they also kill other fast dividing cells such as the hair follicles or the nerve cells. And when the nerve cells are attacked, they manifest as pain and numbness. And looking at the human perspective of it, the patients often report that they feel like walking on air because they lose sensation in their feet. And they report constant pain in the fingertips when they pick up their chopsticks or when they button a shirt. So they undergo constant pain. And while they are trying to overcome cancer, they also develop these very painful side effects. Unfortunately, currently the only modality of treating this is painkillers. So they recover from the cancer, but they end up with lifelong pain, and they have to keep popping these painkillers every day, every few hours. And there is no approved prevention, although there are a lot of research going on in this area. Another way of preventing this from happening is actually stopping the chemotherapy itself. So it becomes so severe that the doctors are forced to cut down on the life-saving dose of chemotherapy for these patients. So how do we tackle this? So we have empathized with what the actual clinical need here is. We then go on to define better on what the problem statement around this clinical need is. So looking at the overall number of patients being affected by this disease condition, we take a look at the number of cancer cases globally. And then we look at the different markets around the world where our solution is going to be targeted and rolled out eventually. We also started working with a clinical partner who is a leader in the world of scalp cooling to prevent hair loss due to chemotherapy. I'll touch upon that in a little bit. So these are all essentially the numbers of patients affected by this disorder and I'm sure, unfortunately, each of us has been in touch with somebody who has gone through cancer and possibly CIPN as well. What are the other possible sort of competing solutions in the market? When looking at it, the solution which is not the best but has been a good work in progress is what you see here. This is essentially a patient dipping their hands and feet into bags of ice, and the idea is that cooling the hands and the legs causes limited blood flow temporarily in the areas of cooling, and that limits the chemotherapy from reaching those areas. Hence, you're reducing the exposure of the areas of concern to the chemotherapy, where potentially the cancer is not present, and you're preventing damage from occurring. So that's the idea behind this. What's the problem in this solution? Of course, as we can all see, the ice melts, so it's not consistent. And one pointer in consideration for that is the chemotherapy is 3 hours long minimally. So they have to keep cooling throughout the duration of the chemotherapy, and which means that they have to change bags of ice every 45 minutes or so. They can use frozen gloves. These are gel packs which can be put in the freezer and then used. They continue to melt as well, which means that they don't receive the same temperature across the whole duration of chemotherapy. So it's unstable, not thermoregulated. But the more painful aspect is the cold pain. Imagine putting your hands and feet into very frozen bags of ice. Is going to be really painful. Apart from receiving intravenous chemotherapy, having nausea, having a headache, and feeling drowsy and whatnot. So can we offer a better way of delivering this treatment in a safe and tolerable way by using our technological expertise? So but then we go on to ideating, looking at parallel solutions. This is where we came across scalp cooling. So scalp cooling has been a standard of care in clinical practice over the past decade. Of course, the research dates back much before that, before it came into main clinical practice and after FDA approval and so on. So Paxman coolers, whom I mentioned, I currently work with and are the global leaders in scalp cooling. They have a product which looks like a scalp cap, and that essentially cools the scalp, the hair follicles, and does the same to prevent chemotherapy-induced hair loss. Can we develop a similar technology for the hands and the feet to deliver safe, tolerable cooling to prevent chemotherapy-induced peripheral neuropathy? So we, in collaboration with the National University of Singapore, the National University Hospital of Singapore, and also Paxman Coolers. So here we have again, kind of trilateral collaboration between industry, academia, and the clinical setting. So many different people from different expertises coming together. We had clinicians who can be oncologists, neurologists, we had nurses, we had engineers who can be biomedical, electrical, and we had design experts who come from a totally non-engineering background. And we had regulatory specialists, we had patent lawyers. So all of these, a very multidisciplinary team came together to bring this project to life. So the early prototypes looked something like this. They started with paper and they went on to low-cost material, and then into the current patient-facing model of the device which we have in the clinical studies. So this is what the current, I wouldn't say the latest version, we have another version after this, but this is what is in clinical trials globally in Singapore and in the US, because we need to, after prototyping, we need to test it to understand how safe, tolerable, and efficacious this is in a large and diverse group of patients around the world before we seek regulatory approvals. And of course, like I said, the iteration part comes in here. We tested these in Singapore. We got inputs on usability and safety efficacy from the patients, went back to the drawing board, incorporated those inputs in our design, made another prototype that gets tested in other clinical trials, and so on and so forth. So this is what I just spoke. That iterative process is what drives the best user-centric design and user-centric technology. And this is just a case study, and this enabling tool can be used in any vertical or technology development innovation process. So just an overview of what we spoke now. We looked at the clinical unmet need, which is CIPN, affecting a large number of patients globally. We looked at existing approaches, which was frozen gloves or ice packs. There are other devices which offer similar treatment but are not catered for a chemotherapy suite, which is very specialized environment, very busy, and these devices often require people to add eyes, and you can't expect nurses who are attending to patients to sit and add eyes to a device. So that was defining the solution, and then we went on to ideating, prototyping, testing, and iterating. And again, this couldn't have been done with just a single person or a single institution. This had to be a multidisciplinary, international, cross-sector collaboration to realize something of this scale. Taking a slight tangent, how do we take lessons from such a project and implement it to a broader, let's say, a career space? And then the rest of my talk talks about how these skills can be used in early career professional sort of setting as well. So my learnings from a team science project summarized into these key points. So I would say that shared vision, like I said, cross-sector, so everybody has to align on what you're trying to achieve as a team. Thinking globally, not only internationally, but also globally in terms of different users and so on. Being curious, especially for those who are starting off early. Equally, those who are mature in the field, because you tend to narrow down on your perspective as you specialize. Listen when there are people talking, presenting different perspectives. It's important to listen rather than just hear. Having an open growth mindset, more important in a world which is, we can't emphasize how rapidly evolving it is. So we have to have that open growth mindset to explore how different ideas can cross-fertilize. Learning the language, I love this because different people with different expertise speak the same word but mean different things. For example, the word cell can mean a different thing to a biologist, can mean a totally different thing to an electrical engineer. So having that sort of, again, ties into listening and sharing in an open way of what you actually mean, asking questions. All these are important that you're aligned on what you're trying to achieve. Embracing discomfort as you go through a project of a large scale, there will be different hurdles. How do you embrace discomfort and overcome that as a team? Building a relationship is foundational to driving success in a project. And finally, again, I love this point of serendipity. You can try as much as you can, but that little element of serendipity, being open to that, is what will add that magic pinch to your project or efforts which you're driving. Again, coming back to design thinking, how can you use this design thinking in your career as a student, young professional, or women in engineering? And for that, let's look at this concept, which is very popular among HR professionals, called a T-shaped professional. A T-shaped professional is essentially what is a combination of depth of expertise and breadth of knowledge. So when you start out in your undergrad, you have one expertise, but what is that which connects you as you move along to add more levels of expertise to your sort of bucket of skills? It's essentially that horizontal, which is your professional skills or your life skills. And this is, again, a graphic of how people with different skills can come together to collaborate. And it's that professional skills, excelling in that can really make you thrive in a field of multidisciplinary innovation, which is becoming more and more important in this day and age. Bringing in the IEEE perspective, I am part of different societies, as you can see here, and I'm sure many of you are involved in several aspects of IEEE. If not, do get involved, because you get so many opportunities to engage in and develop your professional skills through various initiatives in these sort of organizational units or societies. And what are these professional skills? This is just a snapshot of some of them. And these are skills which you can't really learn in a classroom course, you can learn about it, but to actually become excellent in it, to thrive in these professional skills, you need to learn on the ground. And that is where IEEE was very helpful for me in my career to learn and thrive in sort of picking up these professional and essential skills. Skills like reputation, resourcefulness, curiosity, grit. That's a very excellent one. Look it up. Mindfulness, listening to each other, connecting, building relationships, and whatnot. And that goes on to, as you practice, you become better at it. And again, iterative, learn, engage, and iterate and become better at it. So that is what it takes to be a future-ready professional. And this can apply to not only early career professional students, anybody at any stage in their professionals. Keep iterating and reinventing yourself. And with that, I end my talk. Thank you very much, and happy to talk more about how you can engage in different IEEE opportunities, be it in societies or as students, young professionals, and women engineering. Thank you very much for this opportunity.
Yeah, thank you, Dr. Asia. We may open one question. Dr. Chue.
Thank you very much. It's a very inspiring talk. And I'm an IC design profession. So I'm thinking what's your comment for me to apply your design thinking? Give you some background because we are the kind of component level, right? Mm-hmm. So there will be module level, system level, and there will be end product. So we are kind of several layers ahead, behind, before we reach the real customer. So I'm really curious what your suggestion or insight, how we can, your suggestion for me to apply the design thinking in my IC design professional industry. Thank you very much.
Thanks, Dr. That's a tough question, but I'll try to answer it. So I would think that, like you mentioned, there's a system level and you are at the foundational level. So one way of thinking about using design thinking is to think about the user and see how the foundational level can actually amplify and drive the end user needs. And I'm sure as the industry evolves, there's limited scope which you're working with in terms of the IC industry. And however, the applications are becoming limitless. So can the same thing be used in a different way, and so on and so forth. But I would also think about how this can be used in different fields if it's already not been applied. Like some may be non-obvious, so worth exploring as a sort of experiment. So those are some thoughts.
Okay. Thank you. Thank you for Dr. Asia share us the interesting 5-step design thinking methodology. Thank you
very much.
Yeah. Let's move to the next speaker. The next speaker is Professor Tu Wei Zheng from National Cheng Kung University. Professor Tu, she's now the director of Institute of Microelectronics. Her research interest includes graphene-based component, optical and electrical simulation of nano detectors and nano devices, and photo detectors, solar cells, nanoscience, and nanotechnology, and application of quantum dot. So the topic is little defects, big insight, simple AI for better inspection. Let's welcome Professor Tu.
Good morning, everyone. I'm Wei Chen Tu from National Cheng Kung University, and I'm very glad to have the opportunity to be here and share my recent research about semiconductor AI. I think the topic of today, little defects, big insights, is very suitable for describing AI, but I also want to say that the topic is also very suitable for women. But I want to say that I don't use bigger insights. I just use big insight. So that I want to say that I don't compare women to other groups. Okay, so as you know, Taiwan plays an important role in the semiconductor field. So on one side, we want to continuously put the semiconductor manufacturing process toward or below 1 nanometer. But in other side, we are also facing the shortage of the talents. So how can we move forward? Maybe we can combine AI with our creative person people in the world to together facilitate the improvement of semiconductor field. So today, I will introduce the semiconductor imaging processing and take 2 examples for the imaging processing. The first one is how to realize laser induced graphing for virtual keyboard, and another experiment is about low temperature growth graphing for interconnect in the CMOS process. And finally, I will discuss the women in the semiconductor and talk about the participation of women in the industry. So as you know, this is 2 images of semiconductor field, including one is TEM image and another is SEM image. We typically use these 2 images to distinguish our morphology of our semiconductor materials, and also we can calculate the thickness of the semiconductor field by this TEM image. But if we want to get high resolution or more clear picture, we need to take more time for these 2 pictures. So today I will show you how to use the lightweight AI to improve the resolution of TEM imagery and use the AI model to distinguish the specific morphology of this SEM image. So here I will take graphene for example. So why I take graphene? Because as you know, graphene is a 2-dimensional materials with high mobility, high conductivity, and also it is also very suitable for the heat management in the future tiny chips. So here I show you some fabrication method for graphene. The first one is mechanical exfoliation. As you know, we can obtain graphene by taps, by peeling the graphite once time, and then you can get high quality graphene. But the disadvantages of this method is it's time consuming, low yield, and small area. Another method is reduction of graphite oxide. First, you can prepare graphite oxide and use the acid or heat to reduce the graphite oxide to graphene. The advantages of this method is low cost because it is all solution process, and also the process is very simple. But we cannot obtain high quality of graphene. And the common method to obtain graphene is chemical vapor deposition, because we can obtain high quality graphene, high yield graphene, and we can control the quality of graphene by the parameters. However, we need to use the high temperature chamber to obtain or to realize high mobility or high conductive graphene. Typically, we need about 1000 Celsius degree. So if you want to use graphene in the nowadays CMOS process, I think it's very difficult because the temperature is very high. If you want to realize graphene into nowadays CMOS process, we need to reduce the gross temperature to about 400 Celsius degree. That is the second topic of our talk. And the other method to obtain graphene is laser induced graphene. As you can see, we prepare some carbon-based materials such as potato or paper or PI film or PDMs and so on. Then we focus the laser on the carbon-based substrate, and the heat of the laser will rearrange the carbon to the graphene-like structure. So the advantage of this method is the coat is efficiently, and we can control the porosity or the dimension of this three-dimensional graphene. But the disadvantages include we cannot obtain thin or even the monolayer graphene. Yes. As we can see, this is the SEM image of laser-induced graphene. This is LIG. And we can use the different parameters of laser to control the thickness or the morphology of graphene. So after we finish the graphene, we need to use this flexible substrate, graphene on this flexible substrate to realize strain sensor. So we use PDMS to protect our graphene from the oxidation. So we can see this is the final structure of our sensor, including the carbon fiber substrate and the graphene. This is three-dimensional graphene on the carbon fiber. And after we deposit silver electrode, and then we use PDMS to protect graphene from oxidation. And finally, we put this strain sensor on our finger. And as you can see, if we change the angle of our strain sensor, the resistivity of our sensor will be different. So we can use these characteristics to distinguish what is the angle of our finger. For example, this is straight finger, and we can obtain the delta resistivity over resistivity is 0. And if we increase the angle of our finger, then the delta resistivity will increase. And every strain sensor can distinguish 3 different resistivity. So we can put these sensors on our 10 fingers, then we can use this delta resistivity over delta resistivity to realize 30 level of our this ratio. So we can use this different level to realize virtual keyboard input, as you can see. Yes. So we also construct a interface, machine and human interface, to realize this virtual keyboard system. So this is our applications of graphene-based strain sensor. And as I said, because the morphology or the parameter or the structure of our laser-induced graphene will indeed affect the output of our sensor. So we take many SEM images to get the relationship between laser parameters and our graphics characteristics, as we can see. We take I think over 100 SEM images. So we think, how can we improve the efficiency for us to distinguish what area are covered with LIG. So this is the SEM imagery, and I also can mention that we can distinguish the LIG's quality by this Raman spectra, but this is not I want to mention today. And this is the spotlight of our laser. So we can control the pulse per inches, the image density, or the power of the laser to control the quality of LIG. So here we use YOLO architecture for SEM analysis. Actually, we want to distinguish the coral-like three-dimensional LIG for us. So YOLO can be used as a real-time imaging detection model that automatically identifies micro or nanoscale structure. And the key components includes backbone, neck, head, and we use the metrics including precision, recall, specificity, and MAP to identify our model. So the backbone, including C2F and convolution model, this can enable efficient gradient transmission, and the spatial pyramid pooling fast can capture both global and local texture information. So here's the training and evolution metrics based on the confusion matrix, as I said, including precision, sensitivity, specificity, and mean average precision. So here we distinguish YOLO 8 and YOLO 11. So you can see the precision, sensitivity are also over 95%, and the specificity and MAP was also over 94%. So we can see the blue box of this area is what I said, LIG. It is just like a Coral three-dimensional LIG. So we can use the YOLO model to help us distinguish where are the LIG on the carbon fiber substrate. So this is the first example of the applications of AI on the semiconductor SEM images. And next I want to talk is about low temperature growth of graphene by PECVD. As I said, because typically we use CH4 as the insert gas to grow graphene, but the temperature typically over 1000 Celsius degree. So how can we reduce the graphene growth temperature? One method is that we change the carbon source. We change from CH4 to benzene. And then we use plasma together to help break the carbon bond. And after the benzene absorption on the substrate migrated, and then the carbon bonds can rearrange to a graphene structure. So we can effectively reduce the growth temperature from 1000 Celsius degree to 400 Celsius degree. That's to say, we can combine this graphene on the copper foil. We typically use copper foil as a substrate to grow graphene directly into our CMOS process. So as I say, if we continuously reduce the copper internet, no matter width or thickness, the resistivity of the copper foil will be increased. So how can we solve this problem? We can deposit graphene on the copper to reduce the total resistivity of this interconnect. And we also collab with TSMC and use the copper interconnect with about 45 nanometers to realize this improvement. So here's the TEM facilities. And then we take these TEM images to distinguish our thickness of graphene on silicon substrate. And here's the graphene on the SiO2 and silicon substrate. After we grow graphene on the copper foil, we transfer the graphene onto the silicon oxide and silicon substrate. As you can see, we can distinguish or calculate the thickness of graphene. This is monolayer graphene, and this is multi-layer of graphene. And here's the higher resolution picture. But as I said, we typically use much time and money to take these SEM images. So if there is any method to increase the time or lower the cost of our TEM imagery, I think this is very helpful for us. So how can we improve the resolution of TEM images? You can use SERGAN or some eSERGAN or some SPAN AI model. And here I will show you the model we select and use fewer low resolution image database to train the AI model, and finally we can get higher resolution image. So you can see this is the original TEM image, and after we train a model, we can obtain the higher resolution image. So we can see we can get more clear interface from silicon substrate and from the graphic. So we can actually reduce the time we need to take the ESTM image and also reduce the cost. And also, our lab also developed an AI accelerator to reduce the time to take this higher resolution image. So in the future, we will combine the model with our AI accelerator to further reduce the time. So finally, I would like to talk about women in the industry. And this picture, the data of this picture is from the Global Semiconductor Alliance in 2024. And as we can see, most of the company, the first line, most company only has 20 to 29% of workforce for women. And the technical directors, there are 72% of companies. The female technical directors is less than 20%. And 57% of companies, their female technical vice presidents is less than 10%. That means we have much space to encourage our girls, our women into the semiconductor industry. So what is the barriers or challenges of women into the semiconductor industry? It maybe comes from limited recruitment pipeline or insufficient opportunity or some promotion bottleneck. Or maybe in Taiwan, I think the culture challenges are very critical for us because our students, especially in the high school, they typically not choose the semiconductor field. So maybe we can go to our senior high school to talk to them that semiconductor indeed a great industry for them. So maybe we can consider this method for us to encourage students or women students to get into the semiconductor field, including broaden recruitment channels, culture and inclusion reform, or increase the visibility and recognition. And also we can use the institutionalized processes and metrics for improving the future participation of women. So this is the co-founder and CEO of GSA said. He said, if we are going to become $1 trillion industry, we cannot ignore half of the population. I think the half is women. So as you know, AI can help us to see the invisible in matter in semiconductor field. I think the diversity, especially the woman power, not only help us to see the invisible, but also the beauty part. Thank you.
Thanks to Professor Tu's talk. We may open one question. Dr. Chue.
I wonder your SN or TEM picture already in high resolution. So how do you get a better resolution database to train your model?
We can control the parameter as we take the TEM or SEM process. Especially if we control the energy of the SEM facilities, we can get different resolution of pictures. Yes.
Oh, okay, got it. Thank you.
I'm Professor Lee. Chris.
I think something along the line of what Dr. Chue was asking for AI, because you were talking about YOLO in terms of trying to train these data, and because machine learning is very data-driven, so where do you get this sufficient data to train? have you also considered using explainable AI? Say, for example, for the YOLO, you have different scales. That's actually multi-resolution. And
Yeah,
for the
because
data that you have, it's, you can extract morphological features. So is that feasible, like more features?
actually we spent much money to take these TEM and SEM images. Yes, so we for the second example, we take over thousands, over hundreds of TM imagery. But as Professor Lee said, I think this is not enough. So in the future, I will try to get a larger database to train our model to improve the result. Yes, I will consider that method. Thank you. Yes. Yes.
Okay, because we are almost behind the schedule by almost 50 minutes. So if you have any question, you can contact Professor Chu in person. So we finish this session. Thank you.
Thank you. Thank you, Professor Chen. Please give a big round of applause to Professor Chen and our outstanding speakers. And now we'll proceed to the last session of the day. And please welcome our moderator, Dr. Justin Xue, Director of TIARA and also AVP of e-tron Technology, to the stage. Welcome.
Okay. Next speaker, it's my pleasure to introduce Chamika Sudusinghe, who will join us online. Chamika is currently a PhD student at the SIBO School of Computing and Data Science, University of Illinois Champaign, Urbana-Champaign, working with the ADAPT group led by Professor Charis Mendes. His research spans graph neural network acceleration, automatic data selection for learned course models, and sparse accelerator modeling. In 2025, he has published papers at the top venues such as Splash, UPSLA, and EXAC at ICML. Chamika is also deeply involved in IEEE communities. He served as a vice president of product and service for the IEEE young professionals. And he has been honored as an outstanding student volunteer in IEEE Sri Lanka. Please join me in welcoming Chamika to share his insight on Cognate, acceleration of sparse tensor programs on emerging hardware using transfer learning. Let's welcome Chamika.
Thank you very much, Dr. Justin, for the kind introduction. I hope I'm audible.
Yes, we can hear you.
Yeah, perfect. So good morning, everyone. So I'm Chamika. I'm a third year PhD student at University of Illinois. So as Professor Justin mentioned, I'll be talking about one of the recent publications that I have done, which is Cognate, acceleration of sparse tensor programs on emerging hardware using transfer learning. So before going into the topic itself, I just wanted to share about my IEEE journey as well, because there are lots of students listening to me today. So just wanted to highlight what role IEEE can play in your life. So this is a snapshot of my IEEE journey. So I was part of multiple IEEE organization units, because I started in my freshman year when I just joined at the university. So I started from an IEEE student branch at the university, and then similar to IEEE Taipei Section, I was a volunteer at IEEE Sri Lanka Section, and then I was part of IEEE Region 10, where Professor Lee and Dr. Aishwarya are part of as well. And so I was part of the IEEE Region 10 Student Activities Committee, where I was the secretary. And likewise, I volunteered at IEEE Computer Society, now at Systems Council, and now even part of some initiatives within IEEE USA as well. So started at the university, I was able to navigate my journey to volunteer across multiple branches within IEEE. So now today I'm part of IEEE students and IEEE young professionals global committees where I'm serving as a vice chair. So all this happened within 7 years. So if you are new to IEEE, so you are not late. You can start even now, even if you're a grad student or even if you are in your undergrad. So IEEE offers you the opportunity to like volunteer and follow your passion. So for example, you can fail multiple times at IEEE, but you won't be fired. So you can experiment ideas and like try to do things that you find interesting. So that's my IEEE footprint, and these are like 2 images. I just wanted to highlight my early days at IEEE and where I'm now right now. So initially this was back in Sri Lanka where I was with some of my colleagues from the university, and in the picture to the right you can see me in a corner, and as well you can see in the middle Shavi, who presented earlier today, who is the chair of the IEEE Young Professionals Committee. So before going into the topic itself, I wanted to highlight one more initiative at IEEE, so which is called IEEE Elevate, which is done with a similar intention as of the session that we are having today. So bridge theory with practice, how we can like closely collaborate with both academia and industry together with students. So this is a project that we are doing where students are given the opportunity to like work closely with industry and academia mentors to work on short-term projects, and which we call the projects up, and also like we are trying to expand it into like career kickstart and innovation challenges. Career kickstart is for like internship opportunities, and innovation challenges are for hackathons and like sprints. So this is a global program that we want to expand, and hopefully within the next couple of weeks or like during next month, we are planning to open up student registrations. And currently we are recruiting mentors who are interested in like participating in this. So since we have a lot of industry members from Taiwan attending the event today, so you don't need to be an IEEE member to be a mentor. So if you're interested, please feel free to sign up. There you'll be able to work with students on multiple different projects. Yeah. So coming into the topic today, so I want to set up the context initially. So the main discussion point for today is that both workloads and hardware are becoming heterogeneous. So that's an important observation if you look into like multiple innovations that's happening around the world. So for example, let's consider about this image that you see here. So there are like multiple workloads working together. Like we are doing video splitting, we are doing image processing, we are doing text processing, and we are sending it through an LLM to whatever the downstream task that we want to do. So likewise, in today's environments, we are dealing with these multiple heterogeneous workloads in like different setups, and we want to process them faster. And how to process them faster? There we have like multiple programming languages as well as multiple compilers there. So if you are familiar with computer vision, there's this compiler framework called Halide, which we use for computer vision related tasks. And I think you're familiar with TensorFlow, PyTorch, and JAX. JAX is like the newer version released by Google, in where TensorFlow is the predecessor. So those new frameworks are there for like machine learning. And when it comes to like classical compilation frameworks, you might have heard about LLVM and more recently MLIR. So we have these diverse languages and compilers that help us to like process these workloads and send them into multiple hardwares. So looking at the hardware, we have CPUs, GPUs, accelerators, and even pre-silicon accelerators, which we are like using for testing out like multiple novel hardware as well. And coming into commercial hardware, one of the interesting things that we have noticed nowadays is that this hardware have become more or less more or more secretive. So companies are like having their own set of hardware, where Google is coming up with their own version of TPUs. And when it comes to Amazon, they have their own set of hardware accelerators, such as like Trainium and etc. So different organizations are coming up with multiple novel accelerators, which are like very specific to their frameworks. So when it comes to the broader context, we have multiple workloads, we have diverse programming languages, and we have heterogeneous hardware. So the goal today, in the context of large language models as well as this machine learning, is to execute these heterogeneous workloads in a way that they are executing correctly as well as they're executing efficiently. So how to do that? The answer is already there. In the image itself, we have compilers. So when it comes to compilers, what we have been doing most of the time is whenever we are coming up with a novel hardware, we develop its own compiler backend. So for each hardware, we have a different compiler. For example, Google have their own, Amazon has their own. So likewise, there are like multiple different compilers that are out there. However, these compilers, building them manually is not the most efficient way to do it. A few reasons, if I point out, is like it requires a lot of engineering effort. So whenever we are doing a change, we have to doing at the hardware level, we have to change the compiler. And if we like change the hardware entirely to a novel version, let's say we went from like TPU version 1 to TPU version 4. If we are going from 1 to 4, we might have to like change the compiler entirely, like based on like how the hardware is arranged, like whether we are dealing with, whether we are changing the scratch pad memory or whether we are changing the caches, we might have to change. And the second point is like hardware is moving fast. So we are trying to make hardware more efficient, especially when it comes to inference. So compilers which are not evolving faster can become stale. And then you might know that we have different optimizations that we want to do. And if you are familiar with the phase ordering problem within compilers, so how to figure out these optimizations, we need to have these compilers working efficiently to figure this out. So the question is, how can we make compiler construction for this novel hardware evolvable? So the answer to that question is we go for automated compiler construction. So if you are not familiar with compilers, I have added a sentence here. A compiler is a software tool that translates human readable source code into high-level programming languages, in high-level programming languages into low-level machine code that computer processor can execute. Simply like, let's say we have C++, Python or Java code. We use a compiler to like translate it to machine code where the computer can like execute it. And automated compiler construction is a strategy that we can use. So rather than like coming up with a compiler manually, we come up with the compiler automatically. So when it comes to automated compiler construction, so let's look into like an optimization pass within the compiler. So what it does is like it gets some code, it do some optimizations, and it outputs the code that can be read by a machine. And when it comes to optimizations, as I mentioned earlier, like previously, like we want these optimizations not to change the initial code that we have written. So for example, let's say initially we want to do matrix multiplication. So after doing these multiple optimizations within a compiler, if the answers are not correct, there's no point of doing that. So we want to make sure whatever the optimizations that we explore to be correct. So that's why I mentioned here like semantically equivalent transformations. So whenever we do something on top of the code that we have, we want to make sure that's correct. Then we have these optimization strategies that we can explore. So that can be like loop strip mining, loop tiling. If you're familiar with GPUs, you might already know what tiling is. And then we have multiple other optimizations that we can do. And which order we need to do that, that's regarding the phase ordering problem that I have mentioned before. And the third point is like cost models. Cost models means that let's say we have 10 different transformations that we can do for a certain optimization. And then let's say we have 10 such optimizations. So altogether, like we have like 100 choices. So one of the ways to figure out what's the best choice is to execute this in hardware, get numbers and figure out this is the best one. So I'm going with this version of the program. So that's not optimal always, because we cannot go through all these different iterations of programs. A way to figure that out is like having cost models. So these cost models have been developed using heuristics initially. So a way to like figure out these cost models to like work automatically is by having these cost models developed using machine learning based techniques. So going into this slide, I wanted to mostly highlight about this cost model part, because that's where like most of my research is focused on. So we have this transformation space, which has to be correct, which is like which we can automate using programming logics. And then we have the optimization strategy and the cost models, where we can use techniques such as machine learning. Why I think machine learning can be used here is not because I am the first one doing it, but already companies such as Google are exploring these techniques. So there's this Google's TPUs where they have used this machine learning based cost model for like tiling as well as tiling. So why it is important for us here today when it comes to the accelerator setup I'm going to talk about next. So here are like 3 of my research interests broadly. So the first one is like what we are focusing today, learning data efficient cost models that generalize across architectures. And another one is like scaling scalable techniques for accelerating system level optimization using ML. And finally, how to take robust compiler decisions under different sparsity levels and structural variations of the inputs, which we are going to discuss later in the topic as well. So coming into the main topic of discussion today, the main idea for today's discussion is, can we use transfer learning for program optimizations? So the goal is to automatically generate optimal compile optimizations for pre-silicon novel hardware accelerators. And if we look into how we are doing this right now, I have already mentioned a few things that we do. One thing that we can do is like trial and error by hand. So we come up with a new version of hardware and we come up with like a simple compiler or like a simple ISA for that, and we test it, and then we change it here and there a bit, and then we test it again, and likewise we do trial and error. Then a second option that's there right now is like training cost models using large data sets collected from running code. And as I mentioned earlier, Google is already using these machine learning based cost models for their compilers. And an advantage that they have is they have their large data sets, which they can use to train machine learning models, which they are using to within their compilers. But a limitation of both these approaches that are out there right now is they're slow and time consuming. And why this would become a matter, I'll be discussing in the next few slides. So the new idea that I have worked on this work is, can we use transfer learning? So it's simply like, instead of like training cost models on this novel pre-silicon accelerator hardware, can we train cost models on commodity hardware such as like CPUs, and then fine tune the resulting models on a few runs on a simulator of an accelerator? Can this be done? So that's what we are going to explore today. And if this is successful, what would happen is that we'll be able to develop compilers faster, and we'll also be able to like explore more choices when we are developing hardware. So I hope you might be aware of design space exploration, where we go through like multiple choices of like how many processors to use within an accelerator and what should be the cache size. So these decisions have to be made during the early design stages, and we get more flexibility to make these choices if we have a compiler that's working along with the hardware, which will tell us that if you execute it this way, you will get like the least execution time for your input. And if this, why I think this might succeed is because of the common optimizations that are available across hardware. So when we look into these multiple hardware, for example, if we look into like CPUs or GPUs or even our accelerators, optimizations such as like tiling, reordering loops are like common. So these optimizations allow us to transfer some knowledge from one hardware architecture to the other. And the contribution, of course, is an optimized transfer learning approach that leverages the shared features across hardware while mitigating the differences. So now going into the specific area of the study that I have done. So the work that I have done so far are specifically for sparse tensor programs. So if you're familiar, if you are new to sparse tensor programs have become very common across many fields these days. We can find the applications in the fields such as scientific computing, deep learning, graph analytics, and many more. And why optimized sparse code is challenging is due to multiple reasons. Sparsity patterns, which can differ based on how they arrange within the matrix, and different optimizations that we can do, which we call auto tuning. So for example, we can tune the knobs in different ways. And this results in like large search spaces, which can go up to like 10 million choices to select from. So I have shown a reference here. And these needs large data sets, as I mentioned earlier, like can be like up to 2.1 million data points. And when we look into the accelerator setup, we have novel accelerators coming up, which are more configurable. So in the sparse domain, one accelerator is like SPADE accelerator that's developed within UIUC. So it offers us like different architectural flexibility knobs. For example, we can decide whether to do cache bypassing or not. And this accelerator is specifically doing like two optimizations, which are called SPMM and STDMM. Two sparse primitives, which are SPMM and STDMM. And why designing this flexible hardware is hard? So now that we know we can use cost models, can we use the same cost models for these? The difficulty arises from like the time and the cost associated with like getting data points. So sometimes in these accelerators, it can take up to 2 weeks to collect a single data point. So imagine like collecting 2.1 million data points from such an accelerator that can take up to close to 70,000 years. So we cannot use the same techniques that we are using in the CPU domain for these accelerators. That's why we have to explore and see a method like transfer learning would work. So simply, as I mentioned earlier, so we use data from a CPU, train a source model, and then fine tune that source model using a few data points from an accelerator and figure out what the best cost when we give a program and a set of configurations. So the way that we tackle this problem is leveraging both homogeneity and heterogeneity of the hardware. For example, if you look into like the domain of transfer learning, there are like multiple concepts. So one is like heterogeneous transfer learning and one is homogeneous transfer learning. So we kind of extracted both these ideas and exploited both of them to come up with our technique where we use homogeneity to do approximate mapping of comparable code transformations. And we are doing heterogeneous transfer learning using latent encoding of hardware specific optimizations. So as you can see in this image, we are dealing with both these aspects of transfer learning to train models which can learn from common features, at the same time learn the hardware specific features to mitigate the heterogeneity across these architectures. So in simple terms, we are working with like 4 neural networks working together to tackle this problem of homogeneity and heterogeneity. So to explain this further, I've shown you a table where we show what optimizations are common across hardware, at the same time what optimizations are different. So as you can see,
can you hear me? I'm Tracy, I'm the MC today. So because we're already having delay, I would please ask you to probably wrap up in 2 minutes.
Sure.
Thank you.
I should be able to do that. So here we have these multiple optimizations that are working together across these architectures, and I have shown like 2 examples here. And going into the result sections, I have shown that these methods that we have come up with are like significantly better compared to what's out there. For example, if we have used like a traditional transfer learning approach, we would only get like 1.04 speed up. But if we use the technique that I have introduced, it can go up to like 1.4. So the big picture is the techniques that we have introduced can pick up better knobs for programs and improve performance. So more results are available here, so you can have a look at it later, and you can also have a look at the paper itself as well. So in concluding remarks, what I would say, transfer learning enables finding better optimizations for program in novel hardware fast. And the proposed optimized transfer learning framework that we have developed for compiler cost model training works well. And finally, we improves the performance over SOTA by 28.4% on a specific accelerator called SPACE. So that's it from my end, and thank you very much for listening.
Thank you, Chamika, for your sharing on your IEEE life and also your research work. In lieu of the time, so would you mind I skip the Q&A, and I will welcome the audience to send the email for your questions. Thank you. So next, it's my great pleasure to introduce Dr. Jianwei Su, currently a staff engineer at the Industrial and Technology Research Institute, ITRI. Dr. Su received his PhD from the Department of Electrical Engineering, National Tsinghua University, where his research focused on AI hardware and next-generation computing in memory technologies. Over the past several years, he has been a major contributor to the IEEE, ISSCC, and the IEEE Journal of Solid-State Circuits, JSSC, publishing multiple first-author papers on SRAM CIN macros and the AI Edge accelerators. He has also received multiple recognitions, including the ITRI Annual Paper Award for 4 consecutive years, and also the Macronics Golden Silicon Award in 2020 and 21. Today, he will present his talk entitled Enabling Efficient AI Through Next-Generation Computing in Memory Technology. Please join me to welcome Dr. Jianwei Su. Thank you.
Hello, everyone. I'm honored to be here. I'm Jianwei Su from ITRI. Today, I would like to share recent work on how next-generation computing memory technology enable efficient AI. We look at the list technology can how save the low power computing and high performance in AI computing. This is my briefly outline myself. Today, this page shows the outline for my today's talk. First, I will show the background and challenge for AI computing, include the AI computing from cloud to edge, and training computing for notable model, von Neumann architecture bottleneck, new architecture of AI chip CI research program with NTHU. Second, we've introduced EOSL, core competence and application of our technology, CI research in development result. Finally, I will conclude my talk. As you know, AI happens everywhere. AI computing from cloud to edge. We can distinguish the three parts: the cloud computing, fog computing, and edge computing. Cloud computing is the central processing, requires the large transfer used in large language model. Fog computing between the cloud and edge through the internet to network. Fog computing is the distributed processing compute near data source used in smartphone, smart home, and IoT device. Edge computing is distributed processing computing at the data location point. We call the local computing, used in low power sensing and new AI device. So increasing the AI device complexity and quantity, we need a low power consumption and high computing performance AI hardware chip. This chart shows the AI model and most low increase chart. You can see the AI model computing grows the 4.7 times per year, but the hardware based on most low define only 2 times per year. So you can see this two-line gap. So we need a new architecture to bridge this two-line gap. Non-human bottleneck is the memory and the processor element is separate. So data movement between the PE, global buffer, DRAM is the top energy consumption in the chip. You can see the past the reference analysis, the DRAM data movement to the LU cost the 200 times energy cost in the data movement. So non-human bottleneck disadvantage the high power consumption, limited payload, and low memory latency. Non-human architecture disadvantage the high data transfer overhead, low energy efficiency, sequential execution. So the new architecture we call the computing memory. Computing memory is merge the memory and the computing function in the one chip or one main core. Computing memory can divide by the two structure, the digital computing memory or analog computing memory. Analog computing memory means the make calculation is the analog level and store the ADC to read out the output. Digital computing memory means all the function use the digital circuit and store the adder tree to output the data. So computing memory has the advantage the low power consumption, high energy efficiency, and high parallel computation. This page shows the CN research progress. Each cooperate with the National Tsinghua University. We publish a paper in ISCC from 2020 to 2025. We improved the technology node from 28 nanometer to 16 nanometer FinFET. Memory type, we developed the SRAM computing memory and the Gensel memory at 2024 and 2025. And make operation, we use the analog computing, include the current base, charge base, and time base. 2023, we developed the hybrid domain computing memory make and digital domain. We improved the precision from 4-bit, 8-bit to floating point and microscaling format. and improve the energy efficiency from 13 TOPS watt to 118 TOPS watt. Okay, this page shows introduce the EOSL, Electronic and Optical Electric System Research Laboratories. Our have the 15 lab and over 816 staff members and over the 2,600 patent granted. Our research spans from the semiconductor, display, optoelectronic, IC design, and administrative. Our mission is to bridge the research and industry connection to driving the world semiconductor innovation. Within the EOSL, chip design, technology, and design division include the device, circuit, and system. And we have the two labs, narrow electronic lab and sub-terahertz system lab. In device, we develop the non-volatile memory, RF gain nitride, silicon carbide, OS, monolithic 3D OS flat device, quantum circuit include the CIN AI chip, memory circuit, driver circuit, and power amplifier. System in our system development develop the keyword spotting and voice control for verification, the CIN chip, and AI water leak detector. So from device to system, we deliver the total complete and optimize the total solution. In the non-volatile memory, we develop several devices such as the MRAM, RRAM, and FRAM. MRAM has for high performance use in automobile industry use. RRAM for low cost use in consumer. FRAM has the low energy for consumer. MRAM has the phase access, so we can use in the processor. RRAM and FRAM have the low cost and low energy. We can use the IoT edge computing. So edge AI chip needs a low power, high efficient computing, long battery lifetime. For example, the image recognition, in voice recognition has the many run time about the years or months. So we go to extend the battery life by 10 to 100 times. And I think the CIM architecture is a new structure can break through the monument architecture for low power and high efficient edge AI chip. Okay, let me introduce the E3 CIN IP on CIN IP. We develop the CIN IP use the analog domain computing memory, and this macro has some future. We use the technology node, use the 20 nanometer. Macro capacity is 512 kilometer, and we use the core VDD, and CIN attest time is 10.9 nanoseconds. We achieve the high energy efficiency, 20,000 TOPS watts. And this macro use the current mode accumulation. We use the subthreshold voltage applied to the gate to reduce the current, so for high energy efficiency. And we use the ternary weight mapping to reduce the process variation on accuracy. And we use this AI analog CIN apply the voice application. We use the keyword spotting to demonstrate the leaks macro. Okay, if you have the interest in, you can search the ASCC 2021 in IEEE website. This page shows the CNIP2 analog computing. We improve the capacity to 1 megabit, 22 nanometer SRAM base, improve the precision, 4B input, 4B weight, and 5B output, over 5,700 TOPS watt. And also use the current mode accumulation. We extend the transistor to 4 multi-bit 4B input. We use the 4 transistor to implement it. And this macro we use for security. We use the local differential privacy to demonstrate this macro. This macro in algorithm have the one feature is we use the sensor amplifier variation, converge sensor amplifier variation, and time-based confusion to generate the strength dynamic privacy protect. And this paper published in the BSI Symposium 2024. And this is CNIP3. We the same the structure like IP2 analog CIN computing 1 megabit, 22 nanometer SRAM base, 4B input, 4B weight, 5B output, and over 5,800 TOPS watts. And different by IP2, we integrate the group differential privacy and spatial temporal ensemble algorithm in the IP3. This macro published in the BSI Symposium 2025. Okay, our team service provided by Narrow Electronic Lab. We also provide industries server through the Narrow Electronic. This item shows we service the item material process and verification and joint development project and single station service like a backend offline. Our processing is the 8-inch wafer process. And this is my summary. We purpose the idea like a total solution from device, process, circuit to system. Device like MRAM, non-volatile memory, circuit, power amplifier, and an AI chip. We integrate the hardware, software, and we have the system and verification design team. And finally, we transfer the technology to the prototyping for AirPod or smart home situation. We aim to make an AI chip more efficient, secure, and sustainable for a smart future. Okay, this is my talk. Thank you very much.
Any question from the audience? Thank you, Dr. Su, for your introduction. I have a quick question. For your local differential privacy, because you're adding the noise to preserve the privacy, in this application, it requires a lot of data to create a statistic, right? So I wonder, in your application, are you focusing on creating like IoT node at the local and collecting the mass data in the cloud to get the trend or the information from the various IoT? I'm wondering what the application for your deployment. How do you deploy in the real application? Yes, okay. like this one, right? You have this LPD.
Yeah,
and how do you use in the real application?
Okay, this is clearing the photo, and this is a CN chip, and clearing photo input the CN chip. The first step, we remove the some information and quantization. This photo is the 14-bit. We quantization to the 5-bit. And 5-bit, we have the two when we quantization to low bit precision, we have the two paths. The one path we protect lead photo in the chip, so we transfer the data to the cloud. We can protect this information to attack, and the other edge we can do this algorithm to save the information classification with the correct accuracy.
Yeah. Thank you very much.
Right. This is very interesting, especially when you talk about in-memory computing. It's a cross-level of abstraction. Do you mind elaborating? I hope to learn from you how you do system integration and especially verification through these different levels of abstraction. Yes, thank you.
Thank you. First, we define the situation like differential privacy. So we top down the situation and bottom up the device. Our device we use the SRAM base. So we divide the SRAM base and divide the circuit and the system integration from the differential privacy. So we have some problem in the verification because the processor variation. So we in the one chip we have the processor variation, so accuracy just is very important. So in the CM2 we include the calibration mode in the CM chip to improve the accuracy. So we can use the calibration circuit to calibrate the variation to improve the accuracy.
Thank you very much, Dr. Su. Then it concludes our session for two presenters. Yes. So I hand back to Tracy.
Thank you very much. Thank you. Please give a big round of applause to our moderator or to outstanding speakers. Thank you. So that brings to the end of today's program. This is the very first SYW seminar held in Taiwan, and we all know that starting something from scratch is never easy, but it is the effort, the teamwork, and share moments along the way that makes this experience truly meaningful. So please give ourselves a big round of applause. So let's hope that this is just the beginning of a remarkable journey. And with everyone's passion and support, we look forward to welcoming you again in the next SYW seminar. So before we close, the organizers have prepared lunch boxes for all the on-site participants. So you're more than welcome to enjoy your lunch here or take it away with you. So also you're cordially invited to Taiwan Innotech Expo, TIE, at the Taipei World Trade Center, Hall 1. So for those who are attending the opening ceremony of the TIE in the afternoon, please follow Dr. Jiang Zhenglong's lead after lunch. And so please don't go too far away. And once again, on behalf of the organizers, thank you for your participation. We wish you a pleasant day. Thank you.